Hi guys, my name is Driskali Habiba and I'm in 9th grade. Today I'm going to talk about realizability criteria of tied buckets on a grid plane. This section called Applied Mathematics, and my supervisors are Abil Bigzad and Mamar Gul.
So guys, my research objective was to determine the criteria for the realizability of tied buckets on both a flat plane and a torus. We aim to propose a criterion that acts similarly to the famous Pontryagin-Kuratowski theorem, but specifically for buckets. My hypothesis was simple but profound. If a bucket contains certain forbidden sub-buckets, it becomes impossible to realize it on either the plane or the torus. And my scientific novelty was, for the first time, a complete classification of all forbidden buckets has been established for the plane and the torus, one for the plane and four for the torus. These results were obtained through the analysis of the topological properties of buckets. To understand our work, we must first look at what a graph and planar graph is. So, what is a graph? A graph is a mathematical structure used to present connections. It consists of vertices, which are points or nodes, edges, which are lines connecting the vertex. Graphs are used to model many real-life systems such as road maps, computer networks, and social connections. And what is a planar graph, you think so? A planar graph is a graph that can be drawn on a flat surface such as paper without any edge crossing. This means vertex can be placed anywhere, edges can be curved if needed, but edges must not intersect. If edges cross, the graph is called non-planar. And I think that you're asking a question like, why is planarity important in our life or something like that? Checking whether a graph is planar is important because crossing edges make drawings hard to read, and in real life, crossings may require bridges or tunnels. And so, engineers want simple and clear designs. So we need a rule to decide if a graph is planar or not. Kuratowski theorem. Kuratowski theorem gives us a clear answer. It states, a graph is planar if and only if it does not contain K5 or K3 and 3, or any graphs that look like them. These two graphs are called forbidden subgraphs. Why K5 and K3 and 3 matter? These graphs are important because if a graph contains K5 or K3 and 3, it is not planar. If a graph does not contain them, it can be planar. This makes Kuratowski theorem very useful and powerful. Kuratowski theorem is used in many fields. Map drawing to avoid unnecessary crossings, computer networks for clean layouts, electrical circuits to reduce complexity, engineering and mathematics for better design. And if you look at map drawing, what it does. So it helps determine whether a map can be drawn without crossing lines. It helps with reduces intersections and makes maps clear and easy to read. Where it used, you think so? It uses on road maps, subway maps, and transportation networks. Why is it important? It's important because crossing lines confuse people and clear maps are easier to understand. So the K5 graph. Theorem 1. K5 is non-planar because assume K5 is planar. For a planar connected graph, Euler formula states vertex minus edge plus f equal 2. For K5, vertices are 5 and edges are 10. So f equal 2 minus 5 plus 10 equals 7. Summing the number of edges on the boundary of each faces gives 2 edges equal 20. In a simple graph, a face must be bounded by at least 3 edges. Therefore, 2 edges equal 20 more or equal to 3f equal 21. This contradiction proves K5 is not planar. So the K5 graph is called a complete graph. It has 5 vertices. Every vertex is connected to all other vertices. Because there are so many connections, it is impossible to draw K5 on a plane without edges crossing. So, like I said, K5 is non-planar. So, K3 and 3 graph. Theorem 2. K3 and 3 is non-planar as well. If we look at it like we look K5 graph, we can see that K3 and 3 is also non-planar. So K3 and 3 is a complete biparate graph. It has two groups of vertices. Each group has 3 vertices. Every vertex from one group connects to all vertices in the other group. No matter how we draw it, edges will cross. So K3 and 3 is also non-planar. So the results of my project is one forbidden bucket type that cannot be realized on the plane was identified. 4 forbidden bucket types that cannot be realized on the torus were determined. So the conclusion is the research established the realizability criteria of tight buckets on the plane and the torus. This approach contributes to the development of embedding theory in the general case and opens new directions for the topological study of graphs. And this is the end. Thank you for your attention. Goodbye.